Welcome everyone. So this is the part 2 of the session videos where we're discussing the bio and the multi-queue layer. The part 1, which is the video previous to this in the channel, discusses the bio layer and basically the first part here, which discusses the accounting that goes on the bio layer, the two different types of devices, request based and bio based, and then it discusses how recursion can occur in the bio layer and the piece of code and the technique the bio layer uses to avoid that recursion. Right, so it is all there in the first part of the video. In this video, what we're going to discuss is the multi-queue layer, how it attempts to merge the in-flight bio with the requests already sitting in either the plug structure and or the software queues. What is the plug structure? We're going to discuss that concept too, the plugging concept. Next, we discuss the software and the hardware queues, how are they mapped, and how they are basically run. Next, we're going to take a peek into the elevator or the scheduling algorithm, and lastly, we're going to look into the dispatch step, which pushes the requests to the device driver below. So let's dive right into it. So the block MQ layer presents the requests as one or more well-defined streams to the underlying driver. Right, so we will look into the following major things which the block layer does. Uh, Checking and performing a bio bounce, what is bouncing of bios and why it is needed. Creating a request structure or either using the already cached requests. Checking with for bio merging, the elevator sublayer, and the hardware queue dispatching. So one thing I will reiterate here is when the bio is entering the multi-queue layer, it does this through this function called block mq submit bio. Next, we're going to look into the creation of requests. So the requests are the unit of IO in the multi-queue layer, right? So the function that we're looking into, block mq submit bio, either get requests from a cached underscore request list or by allocating a new. For both the cache request and the new request, there is an attempt to merge the bio. So in this step, there are two different types of merges that are attempted, right? First, a plug merge is attempted, which is that the bio is there's an attempt to merge the bio with the requests that are sitting in this plug mq underscore list structure, and the next one attempted is the bio merge, where the requests are sitting the bio is attempted to be merged with the requests sitting in the software queue, and these two are different and they are tried one after the other while creating a new request or getting a request from the cache list. So one thing to note here is for both these tries, in the end the function block underscore attempt bio merge is used. We're going to first look into this function and how the bio is attempted, then we're going to move back to the two different merges and talk a little bit about them. So the function block attempt bio merge checks whether the in-flight bio can be merged in the front or the back of the request. Now that request could have been coming from the plug MQ or the software queue. We're going to see that next, but checking whether it can be merged in the front or back of the request means that it's going to look a little bit like this. So let's suppose the new request is 4, whether it's on the front side or in the back side, it has to exactly fit with that border of the already existing request. Right, now we're going to look into the two different types of merge. The first one that I mentioned was plug merge. First looked into bio merge, where the bio is tried to merge the current bio with the request sitting in the software queue. Right, so obviously this can be checked only for a limited period of time, and the reason is there can be a large number of software queues through which it has to check, and each software queues can actually be holding a large number of requests, and checking through all of them is going to take a long time. And this being the fast IO path, there is usually not much time to spend checking. So in the current kernel code, usually it checks for the next 8 requests and that is it. As I mentioned, there are too many requests, so that just checks for a short period of time. One more thing to note here is that when it's checking this bio merge, it needs to hold software queue spin lock during the check, and this is one of the reasons. No, this is one more of the reasons why you don't want to check through all the requests that are sitting in all the software queues. Next we move into the plug merge, and before we go a little bit into this, we're going to discuss the concept of plugging. So plugging is a concept where there's a time window in which requests are gathered and they are checked for merging, whether they are in incoming more new BIOS can be merged with the requests that have been gathered in the structure. And one more thing is, once they are all done and the plugging stops, then all of them can be submitted in one go to the device driver. Plugging is usually controlled by the layer above, which is supposed to have an idea when it is better to wait for new requests to come and try a merge with, and when it should just stop the merge and flush the request down to be issued to the driver. So beside this, there are some other ways also requests in the plug MQ list can be flushed. For example, when the current process is getting scheduled out, the scheduled code calls this flush. This is done to avoid deadlock. So for example, think of a scenario. It could be that the current process is context switching, and that is why the schedule code was called, and maybe it is context switching for memory to get available, and the way memory could get available or any other resource if the requests in the MQ list plug are flushed and processed. One thing to note here is that since plug depends on the caller, it could be that the requests added to the plug are meant for different queues, and this is going to be a little relevant next when we see the flush code for plug. So usually when a plug flush happens, these requests are submitted to the software queues or the elevator. But there is a special case where the plug flush, all the requests in the plug flush are submitted directly to the device driver. Let's look at the special case and when exactly does this happen. Right, for this special case to happen, three conditions has to be true at one go. First of all, the plug has request from a single queue. Remember that I mentioned that since the plugging depends on the caller, it could be that the requests added to the plug are meant for different queues. In that case, this special case would not be true, and we will move on to submitting the request to the software queue. But in cases where the plug requests are from a single queue, the first one condition is true. The next condition is that the queue has to have no elevator configured, and the third one is the flush has to be called not from the scheduler code. Obviously, when the requests are to be flushed directly to the device driver, and you do not want the scheduler code to be doing that, because you don't want your scheduler or context switching code to go inside the call to move to the device driver, and subsequently the call to move to the device underlying. You don't want your scheduler code to have such a long call going through functions. Right, when all of these special case conditions are true, then either of the below functions submits the requests directly to the device driver. If any of these conditions are false, then the function blockmq dispatch plug list is used. So this is for the plug flush case, and now we're going to move back to our function blockmq submit and look at what happens after the merge is attempted. And we're going to have this small recap which is going to cover the next few cases. So we've already looked into the bounds, why it is done. Then we've looked into getting a request either from the cached request list or creating a new request. Both of them tries to attempt a plug merge or a bio merge, and both of them end up in this block attempt bio merge function. Once that is done, this function is called block mq bio to request, which converts the bio to the request structure, copying all the relevant details. And this is the last if else that happens, where if there's an active plug, then the request is added to the plug and returned. If that is the case, the request would be flushed down later, as we saw, when the plug stops or through some other means like the schedule code. The next one is if there is an elevator or dispatch busy, which we're going to look into a little bit later. Then it's going to use this function called block mq shed insert request. And lastly, if in the else branch, it's going to again try to issue the request directly to the device driver. Now when I say issued directly to the device driver, I want to repeat that I meant the code ultimately calls the .q_rq of the block mq op structure, which was used while creating the block device, since this is a request based block device. So now we're going to look into the queues where the request first lands, which first is the software queue. We're going to reiterate a little bit again just to make sure we know where we are standing. So the request gets inserted in the software queues from a number of places, right? So either from during a plug flush, and when the three conditions were discussed, then it goes through the above layer and directly gets issued. But if they are false, then it goes to the block mq shed request discussed in the previous slide and gets into the software queue. So one more thing I want to note here is that, as discussed in the first session that we did, the software queues are usually equal to the number of CPU. Hence, the queue which is selected, the software queue number which is selected for inserting the request, are picked depending on the process CPU that the process is running on. And from that software queue number, the hardware queue is picked according to the mapping. Now this mapping is usually defined in this block mq queue map structure, and there is I'm not going to delve a little more detail into this because this would start becoming a very long thing, but just know that there can be more than one number of structure of this type. Sometimes it's just one structure for both read and write requests. Sometimes read have its own map, and sometimes there's another map for polling, where the block mq layer doesn't want to wait for the device driver to call back the completion, and so that the mq layer can poll for completion requests, which makes it faster. And usually how these map structures are arranged is that it's an array where the index is the software queue number and the value inside the array is the hardware queue number, and that is how mapping is done between software queues and hardware queues. Next, we're going to look into the elevator part. So the multi-queue design has a pluggable elevator design, right? And elevators are basically scheduling algorithms. So if the queue has an elevator algorithm configured, then the requests are inserted and dispatched using the elevator defined functions in the struct elevator mq ops structure, right? So a little bit about the name. The name elevator sounds a little weird for a scheduling, but it actually comes from an old disk scheduling elevator algorithm. That's how it was named, which was used to determine the motion of the disk's arm and the head. So from this elevator MQ op structure, the two of the most important ones are dot insert request and dot dispatch requests. The former adds a list of requests to the software queues, while the latter chooses a request to be passed to the given hardware queue. Right? If the insert request is not provided, the requests are simply appended to the list. If dispatch request is not provided, requests will be collected from any staging queue that is configured to feed to this hardware queue, and these are passed down in arbitrary order. Linux kernel has three main multi-queue schedulers: the MQ deadline, the BFQ, budget fair queuing, and Kaibar IO scheduler. I'm not going to be discussing the details of the schedulers here because it's going to be very long, and it frankly deserves a session of its own. Just know that there are some generic information available for how the schedulers work in LWN and in Linux documentation. You can refer to it for now, and when we get into a session for these schedulers, you can come back. So next we're going to look into the pending bit. So when the requests are gets added to the software queues, uh, be it while it is created from block MQ submit request, at that time a bit is set, which is in the HCTX context called CTX underscore map. Right, this is done through the function block MQ HCTX mark pending. This marked bit is checked when requests from the hardware queue are to be dispatched, and what it means is if the bit is on, there is a pending request in that software queue. Right, so this will be used and discussed later when we discuss hardware queues and how they are run. So next we move on to the hardware queue run. The central function to this is this block MQ run hardware queue. That is the core of dispatching requests from the hardware queues to the device driver. Looking closely at this function, we see that it first checks the exact same bit that we just discussed, and what means it checks whether there is a need to run the hardware queue or not. And when I say run the hardware queue, meaning whether there are pending requests in the software queue or not. And if there are pending requests, then the function block MQ delay run hardware queue is called. So this function, this ends up running block MQ underscore block MQ run hardware queue function. Now this can either be called directly or through a block layer daemon, depending on whether the calling function is telling it the call should be async or sync. The above function underscore block MQ run hardware queue ends up calling the block MQ shed dispatch request function. Now we're moving into the last steps. So the function that we just discussed, it either calls .q underscore rq directly, which moves the request to the device driver. It calls this directly through this block MQ dispatch request list, or it calls the schedulers dot dispatch request function. Depending on whether the queue is configured with the scheduler or not, and this happens through block MQ do dispatch shed. So one more thing to note here is that the hardware queues itself maintains a list of pending requests, and every time the code for this is run, it first prefers the requests that are in this pending list over the requests that are in the scheduler. The logic here is that once the request is taken out of the scheduler, the uh, chance of it getting merged or the chance of it getting submitted in one go is lost if the chance of it getting scheduled over each other is getting lost. So unless we have pending request in this hardware queue itself, the request from the scheduler is not gonna get touched. So we're gonna recap a little bit for the hardware queue run loop here. So it starts with this central function blockmq run hardware queue, and that calls this blockmq delay run hardware queue, and it both of the paths here end up into this blockmq run hardware queue function, but either directly, or if it is called async, then there's a work queue daemon called kblockd, and it goes through this, but it ends up in the same function. And the next two functions are dispatch requests and dispatch underscore dispatch requests, and both of them uh, uh, co- end up calling either the scheduler's dispatch code, or if there's a no scheduler configured for the queue, it calls directly the dispatch request list, and both of them end up in this .qrq function, which is the underlying device drivers function call. One last thing to discuss here is the hardware queue performs a bit of flow control here. So the HCTX structure maintains a member called dispatch busy, which is used to control the sending of requests to the device driver. It is an exponentially weighted moving average. So the device driver below can, for example, signal back to the MQ layer that is running low on resources, and to process any more requests it cannot do it. Maybe it's running out of resources or something, and it can signal this back to the MQ layer by sending back block STS resource flag to the .qrq function that gets called. And what happens is when the block MQ layer receives this flag, it updates the dispatch busy param to increase, and every time a hardware queue is run, this dispatch busy parameter is checked, and if it is positive, then the block MQ layer slows down of dispatching of requests to the device driver. There are places where you would notice that if the dispatch busy param is set, then the block MQ code is going to just pick up single requests and send them one at a go. When the requests are completed and there is no flag of STS resource being sent back, some calls to this dispatch busy updation would end up it the value of it going down to 0, and when that happens, the regular flow of request resumes. And this is the last bit that I want to discuss in this session, and this is a little bit about us. If there's anything you want to reach out to for, you can write us an email, follow us on LinkedIn and YouTube for more sessions and news and posts.